we wait for the people to queue. Well, hello everyone. I'm Tomas. Currently a scientist at NORLab in the south. So if you ever go to Rubin, you can hit me up. Presenting a poster on the shadowing of the Einstein probe with CTF. So basically, the main issue is that Einstein probe has been revolutionary, detecting a bunch of X-ray flares. In the first year, detected around 130 of them, but only 10% of them have optical counterparts. So we're trying to address this problem, trying to identify these optical counterparts a little bit faster. So for that, we're using the Zwicky Transient Facility. This was supposed to be a GIF. It's supposed to move. But basically, we're scheduling CTF tiles, basically, to follow up Einstein probe. We're doing it contemporaneously. So we are currently at 4 new sources. 2 of them are afterglows, and 2 of them are supernovae. So if you have questions, come talk to me at the poster.
All right, thanks, Tomas. And next we have Rodrigo.
Hello, I'm Rodrigo Angulo. I'm a grad student from Johns Hopkins. I'm here to talk about the poster I'm presenting on constraining Cas-A shock breakout with infrared echoes. So quickly, Cas-A, youngest core collapse remnant in our galaxy, great object to study for remnant physics. However, this is actually a supernova that was missed. That's where light echoes and infrared echoes come in play with their unique geometry and a path difference. We're able to have a second chance to absorb these historical events with modern instrumentation. Previous studies, such as scanning spectra on scatter light echoes, gave us the type 2b of Cas-A supernova. Previous studies on infrared echoes gave us that UV radiation, i.e. shock breakout. It's the cause of those infrared. And so come check out my poster to check out how I'm analyzing these infrared echoes with these JWST images, and I'm able to get an upper limit on shock breakout duration, which is highly tied to progenitor size.
Hi, I'm Chen. I'm from Tsinghua University, and I studied the common envelope evolution. Recently, I applied our radiation hydrodynamic model to common envelope evolutions, and we find that the radiation pressure could be a main source of driving this envelope to unbind the massive envelope, the envelope in massive binary stars. And we also applied this model to a recent transient named AT2024 ABAO, the luminous red nova, and we use this model to predict, to constrain its progenitor and the ejected mass and obtain reasonable results. You can check our poster on it's number 5. Thanks.
Hi, I'm Kostav. I'm a final year PhD student here at Caltech. So we know that the fate of a star is primarily decided by its stellar mass. So stars that are, say, less than around 8 solar masses fuse up to carbon oxygen and their lives as white dwarfs. Stars above around 12 solar masses fuse up to iron and their lives as core collapse supernovae. However, the boundary between white dwarf formation and neutron star formation is not very clear. The fate of stars in this intermediate mass range is very uncertain. Stellar evolutionary tracks predict either the track at the top or the bottom. They could also fuse up to oxygen, neon, magnesium, and end as heavy white dwarfs or electron capture supernovae. You should also care because they make up roughly half of all massive stars that should explode. So in this work, I used the largest volume limited survey with ZTF to explore low luminosity core collapse supernovae, which are a possible outcome of some of the stars. If you're curious, please come and chat with me. Thank you.